Turns out that in 2022, a fridge-sized probe named DART smashed into asteroid Dimorphos and knocked it off course by a jaw-dropping 32-minute orbital shift, the first time humanity physically steered a celestial body. That single cosmic punch proved we're no longer spectators in the universe, we're players with a game-changing playbook. Here's the kicker: just one gentle nudge a decade early can send an extinction-level asteroid harmlessly past Earth. Did you know a spacecraft weighing less than a truck can rewrite planetary fate? The DART mission. On a seemingly ordinary autumn day in 2021, humanity quietly launched what would become our species' first real attempt at cosmic self-defense. But nobody could have predicted just how dramatically we'd exceeded our wildest expectations. The Double Asteroid Redirection Test, better known as DART, wasn't just another space mission collecting dust samples or taking pretty pictures. This was different. This was us literally punching an asteroid in the face to see if we could save ourselves from extinction. The target was Dimorphos, a football stadium-sized moon orbiting the larger asteroid Didymos, sitting safely 7 million miles away from Earth, far enough that we couldn't accidentally cause an apocalypse while learning how to prevent one. For nearly a year, this refrigerator-sized spacecraft traveled through the cosmic void with one simple job: crash into an asteroid at 14,000 miles per hour and see what happens. Scientists expected a gentle nudge, maybe shortening Dimorphos's 11-hour 55-minute orbit by about 10 minutes. That would have been revolutionary enough. But when September 26, 2022 arrived and DART completed its kamikaze mission, the results left every space scientist on Earth speechless. The orbit didn't just change by 10 minutes, it changed by 32 minutes. 3 times more than predicted. Suddenly, we weren't just capable of planetary defense, we were apparently really good at it. Impact Results Analysis. 3 weeks after DART's spectacular collision, scientists around the world were hunched over their telescopes, frantically trying to figure out why their carefully calculated predictions had just been obliterated by reality. The Johns Hopkins Applied Physics Laboratory had expected a modest 10-minute change in Dimorphos's orbit, a result that would have made headlines and proven humanity could defend itself against cosmic threats. Instead, their instruments were showing something that seemed almost impossible. A 32-minute orbital shift that left astrophysicists questioning everything they thought they knew about asteroid impacts. Ground-based observatories from Chile to Hawaii confirmed the same jaw-dropping numbers, while NASA's Deep Space Network tracked the aftermath with unprecedented precision. But here's where the story gets absolutely wild. This wasn't a measurement error or some cosmic fluke. The enhanced momentum change was real, and it was caused by something nobody had fully anticipated. When DART slammed into the loose, rocky surface of Dimorphos at 6.14 kilometers per second, it didn't just create a simple crater like hitting solid bedrock would. Instead, it triggered a massive ejection of debris that continued streaming away from the asteroid for weeks, acting like a natural rocket engine pushing Dimorphos even further off course. The European Southern Observatory captured spectacular images of this debris tail stretching across space, resembling a comet's magnificent plume, but created entirely by human engineering rather than solar radiation. Momentum enhancement discovery. What started as a simple physics equation suddenly became the key to unlocking one of space science's biggest mysteries: why DART's impact was so devastatingly effective when it should have been just a gentle tap. The answer lies in something called the momentum enhancement factor, a concept that sounds boring but represents one of the most exciting discoveries in planetary defense history. When DART crashed into Dimorphos, it didn't just transfer its own momentum like a billiard ball hitting another ball. Instead, it created something far more powerful, a continuous rocket-like thrust that kept pushing the asteroid long after the initial collision had ended. Scientists at NASA's Goddard Space Flight Center calculated this enhancement factor to be between 2.2 and 4.9 times stronger than the direct impact alone, meaning the debris cloud was doing most of the heavy lifting and changing the asteroid's path. This wasn't just space dust floating away, it was high-velocity material ejected at hundreds of meters per second, creating thrust in the opposite direction, like a natural engine firing for weeks. The Lowell Observatory tracked this phenomenon as chunks of Dimorphos continued streaming away from the asteroid, each piece adding to the momentum change. What makes this discovery absolutely game-changing is that it proved asteroids aren't just sitting ducks waiting to be pushed around. They're dynamic systems that can amplify our defensive efforts in ways we never imagined possible, turning a modest spacecraft impact into a cosmic home run. Asteroid structure insights. When DART obliterated its target, it accidentally solved a decades-old puzzle that had been driving asteroid scientists absolutely crazy. What are these mysterious space rocks actually made of? The impact didn't just change Dimorphos' orbit, it literally tore the asteroid apart and revealed its deepest secrets in real time. What scientists discovered completely revolutionized our understanding of asteroid composition and structure. Dimorphos wasn't the solid, monolithic rock that many had imagined, but rather what researchers call a rubble pile, essentially a loose collection of boulders, pebbles, and dust held together by nothing more than weak gravitational attraction. When DART struck this cosmic sandcastle at 14,000 miles per hour, it triggered a cascading avalanche effect that continued for months afterward. The European Space Agency's telescopic observations showed material continuously streaming away from the asteroid, creating a debris tail extending over 10,000 kilometers into space. Ground-based observatories worldwide, including the Atacama Large Millimeter Array, detected spectroscopic signatures revealing the asteroid's internal composition as chunks of ancient rock that had been floating together for millions of years. This discovery was absolutely crucial because it meant that similar rubble pile asteroids throughout our solar system might be far easier to deflect than anyone had dared hope. The loose structure that made Dimorphos vulnerable to cascading destruction could be humanity's greatest advantage in planetary defense, turning what seemed like our biggest cosmic threats into surprisingly manageable targets for future deflection missions. Strategic implications. When DART succeeded beyond everyone's wildest dreams, it didn't just prove we could defend Earth, it instantly made every existing planetary defense strategy completely obsolete overnight. Military strategists, space agencies, and international defense organizations suddenly found themselves staring at calculators showing numbers that seemed too good to be true, forcing them to tear up decades of carefully planned asteroid deflection scenarios. The Planetary Defense Coordination Office at NASA immediately began emergency revisions to their threat assessment protocols, realizing that their previous models had been based on fundamentally flawed assumptions about asteroid behavior. If rubble pile asteroids like Dimorphos could be deflected with 3 times more efficiency than predicted, then the minimum warning time needed to protect Earth from cosmic impacts had just been dramatically reduced. But here's the twist that kept defense planners awake at night. This incredible effectiveness came with a terrifying flip side. While rubble pile asteroids might be easier to deflect, solid metallic asteroids could prove nearly impossible to budge with current technology. The International Asteroid Warning Network frantically began updating their classification systems, realizing that asteroid composition was now more critical than size when determining threat levels. Countries like China and members of the European Space Agency announced accelerated development of their own planetary defense capabilities, recognizing that the DART mission had just shifted the entire geopolitical landscape of space security. What started as a simple test had accidentally triggered a new space race focused not on exploration, but on survival. Hera mission planning. Before DART's debris had even settled, space agencies across Europe were already scrambling to launch the most ambitious forensic investigation in cosmic history, a mission that would turn the impact site into humanity's first crime scene analysis laboratory in deep space. The European Space Agency had been planning the Hera mission long before DART exceeded all expectations, but the spectacular success suddenly transformed what was meant to be a simple follow-up into the most crucial space mission of the decade. Scheduled for launch in October 2024, Hera carries 2 revolutionary CubeSats named Juventus and Milani that will act like cosmic detectives, examining every detail of the crater DART blasted into Dimorphos' surface. These aren't just ordinary satellites. They're equipped with ground-penetrating radar, advanced spectrometers, and precision imaging systems capable of mapping the asteroid's internal structure down to the meter level. Hera will spend months hovering around the Didymos system, measuring exactly how Dimorphos' mass, shape, and rotation changed after the impact, while its CubeSats deploy to different positions for triangulated analysis. The mission's primary goal is answering the million-dollar question that DART left hanging. Exactly what happened during those crucial milliseconds of impact that caused such an unexpectedly powerful deflection? ESA's scientists need this detailed forensic data to calibrate their computer models for future planetary defense missions, because the next asteroid heading toward Earth won't be a test. It will be the real deal and will need every advantage possible. Planetary defense evolution. So September 2022 marked the exact moment when planetary defense stopped being science fiction and became humanity's newest branch of warfare, not against each other, but against the universe itself. The success of DART, honestly, sent shockwaves through the global space community that extended far beyond NASA's laboratories, fundamentally reshaping how every nation on Earth approaches the existential threat of asteroid impacts. What had been theoretical discussions in academic conferences suddenly became urgent strategic priorities, requiring immediate international cooperation and massive funding allocation. The International Asteroid Warning Network found itself at the center of a completely new type of arms race, where the goal wasn't military dominance but species survival. Countries that had never seriously considered space-based threats began establishing their own planetary defense programs almost overnight. China announced plans for their asteroid deflection demonstration mission by 2030, while the European Space Agency accelerated development of the Fly-Eye telescope network, designed to detect potentially hazardous objects decades earlier than current systems. Even smaller nations started contributing to global asteroid monitoring networks, recognizing that cosmic threats don't respect international borders. The United Nations Office for Outer Space Affairs established new protocols for coordinating planetary defense responses because, unlike any previous human challenge, asteroid deflection requires unprecedented global cooperation. Military strategists from around the world began studying DART's results not for weapons development, but for understanding how kinetic impactors could be scaled up for larger threats. The mission had, kind of accidentally, created a template for humanity's first truly unified defense system against an external threat that could end civilization as we know it. Mission success redefinition. Sometimes the most spectacular victories create, well, the most dangerous problems, and DART's overwhelming success forced scientists to completely rewrite the rulebook on what actually counts as mission success in planetary defense. The 32-minute orbital change that had everyone celebrating suddenly became a cautionary tale about the double-edged sword of, exceeding expectations in space. NASA's Planetary Science Division found themselves facing an unprecedented challenge. If a relatively small spacecraft could alter an asteroid's path by more than 26 times the minimum success criteria, what happens when we need surgical precision rather than overwhelming force? The original mission parameters had been designed around achieving at least a 73-second orbital change to prove the concept worked, but the massive 1,920-second shift they actually achieved revealed a, honestly terrifying reality about real-world asteroid deflection scenarios. Mission planners at the Johns Hopkins Applied Physics Laboratory began developing entirely new modeling software to predict these enhanced momentum effects for different asteroid types, because the next deflection mission might need to thread the cosmic needle with millimeter precision. The problem isn't just hitting an asteroid anymore, it's hitting it with exactly the right amount of force to save Earth without accidentally creating secondary threats or debris clouds that could, persist for decades. Future planetary defense missions will require computer simulations so accurate they can predict not just where an asteroid will go, but exactly how fast it'll get there. Because in real emergency scenarios, there's just no room for pleasant surprises that exceed expectations by 2,600%. Debris management and safety concerns. Nobody expected DART's triumphant asteroid collision to create humanity's first cosmic littering problem. But the spectacular debris cloud streaming away from Dimorphos suddenly forced space agencies to confront an entirely new category of planetary defense complications. While the 10,000-kilometer debris tail looked absolutely magnificent through telescopes and proved the mission's effectiveness, it also revealed a sobering reality about large-scale asteroid deflection operations. Every successful impact creates a potentially hazardous cloud of high-velocity fragments that must be tracked and managed for months or even years afterward. The Space Surveillance Network found itself monitoring hundreds of debris particles traveling at several hundred meters per second, each piece following its own unpredictable trajectory through space. For future missions involving Earth-crossing asteroids, this debris management challenge becomes exponentially more complex and dangerous. Mission planners at NASA's Jet Propulsion Laboratory realized that deflecting a kilometer-wide asteroid heading toward Earth could create millions of fragments, some potentially large enough to cause regional devastation even if the primary threat is eliminated. The European Space Agency's debris tracking models showed that impact-generated fragments could persist in unstable orbits for decades, creating long-term navigation hazards for spacecraft and satellites. This discovery forced planetary defense strategists to develop entirely new protocols for debris field prediction and fragment trajectory analysis, because saving Earth from one cosmic threat while accidentally creating dozens of smaller ones would be a Pyrrhic victory of cosmic proportions. The irony wasn't lost on anyone. Humanity's greatest defensive success had also created our first lesson in responsible cosmic debris management. Precision requirements for real threats. The clock is ticking faster than anyone realized, and DART's incredible success just taught us the most sobering lesson in cosmic defense. Early warning isn't just important, it's literally the difference between survival and extinction for our entire species. When scientists calculated what DART's 32-minute orbital change would mean for a real Earth-crossing asteroid, the numbers were both thrilling and, honestly, terrifying. That same deflection force applied to a genuine threat detected 10 years in advance could alter its trajectory by thousands of kilometers, easily sending it safely past our planet. But here's the nightmare scenario that keeps planetary defense experts awake at night. If that same asteroid were detected just 6 months before impact, even DART's spectacular performance wouldn't be enough to save us. The Center for Near-Earth Object Studies at JPL now emphasizes that the precision requirements for real threats make early detection more critical than ever before. A deflection mission launched decades in advance needs only a gentle nudge, while last-minute interventions require devastating force that could fragment the asteroid into multiple city-killing projectiles. The Catalina Sky Survey and linear detection programs are being dramatically expanded because DART proved we have the technology to defend Earth, but only if we spot the threat with enough time to act. The mission's legacy isn't just that humanity can change an asteroid's path, it's that we must find every potential killer asteroid years before it finds us, because in planetary defense, timing isn't everything, it's the only thing that matters. And that's the incredible story of how DART didn't just hit an asteroid, it revolutionized humanity's cosmic defense strategy and proved we're ready to protect our planet from extinction-level threats. The universe just got a little less scary, and space just got a lot more exciting. If you enjoyed diving into this mind-blowing mission, smash that subscribe button and hit the bell icon so you never miss our latest space discoveries and tech breakthroughs here at InnoVision Tech. Drop a comment below. What do you think about humanity's first successful planetary defense test? Until next time, keep looking up.